my talk is on polynomials and the spectral radius of hypergraphs. My talk has three parts. First, I will give some definitions. Second, I will give some results on tensors and hypergraphs. In the last part, I will give my main results. Our main results is to characterize extremal hypertrees with given size and the strong stability number. First, some definitions. A hypergraph consists of its vertex site V and edge site E. Edge site is a subset of its power site of vertex site. A hypergraph may be viewed as a special case of block design, also set system. A hypergraph is R uniform if every edge contains exactly R vertices. A hypergraph is linear if any two edges share at most one vertex. A cycle. By a cycle of a hypergraph, we mean closed walk. Closed walk such that our vertices V1 up to VL are distinct, and our edges E1 up to EL are distinct. A hypergraph is called a hypertree if it is connected and has no cycle. A similar definition for graphs. A subset, a vertex subset or edge subset is called independent if no two of its elements are adjacent. The diameter of a connected hypergraph is the maximum distance among our vertices of hypergraph H. For a vertex V, we denote by EV the set of edges containing vertex V. The cardinality of the site EV is the degree. It's called the degree of the vertex V, denoted by this notation. For two positive integers R and N, a real tensor A of order R and dimension N refers to a multi-dimensional array, also called hypermatrix, with real entries such that each entry has R subscripts. Each subscript is from 1 to N. Let A and B be dimension N, order R. R is more than or equal to 2, and order K. K is more than or equal to 1 tensors. The product of two tensors A and B is defined to be the tensor C of dimension N and order R minus 1 times K minus 1 plus 1. Its entries is like this. If B is an ordinary vector, so K is 1. So we can K is 1. So the product of a tensor and a vector is a vector as well. In 2005, Qi and Lin independently introduced the concepts of tensor eigenvalues. Let A be an order R dimension tensor. X is a vector. If there is a non-zero vector, if this equation is satisfied, then we call lambda an eigenvalue of tensor A, and the vector X, the non-zero vector X is called an eigenvector of tensor A corresponding to the eigenvalue lambda. So when R is equal to 2, this is just the definition for matrix eigenvalues. So this can be seen as an extension of matrix eigenvalues. The spectral radius of tensor A denoted by rho of A is the maximum modulus of the eigenvalues of A. The characteristic polynomial of a tensor A is defined by Qi in 2005. The characteristic polynomial of A is defined to be the resultant. The notion from algebraic geometry is defined to be the resultant of the homogeneous polynomial system. There are two fundamental results on eigenvalues of tensor. Number lambda is an eigenvalue of tensor A if and only if it is a root of the characteristic polynomial of tensor A. The number of eigenvalues of tensor of order R and the dimension n is this number, n times R minus 1 to the n minus 1. This is a fundamental result can be viewed and extension and the generalization of Pyron-Forbin theorem for non-negative matrix. Now it's for non-negative tensors. Let A be a non-negative tensor of order R and dimension n, where these numbers are greater than or equal to 2. Then the spectral radius of A is an eigenvalues of tensor A with the non-negative eigenvector corresponding to it. If A is weakly reducible, then the spectral radius of A is a positive eigenvalue of A with a positive eigenvector X. First of all, the spectral radius is a unique eigenvalue of tensor A with a positive eigenvector. And vector X is a unique positive eigenvector associated with the spectral radius up to a multiplicative constant. This is the definition of adjacency tensor of hypergraph. Let H be an R-uniform hypergraph on n vertices. The adjacency tensor of H is defined as order R and the dimension n tensor whose entries is defined like in this manner. If this subscripts is an head edge, is a head edge is equal to O1 over R minus 1 factorial. Otherwise, it is 0. The spectral radius or eigenvalues of hypergraph H is defined as the spectral radius or eigenvalues of its adjacency tensor. In this talk, the spectral radius of H is denoted by rho of H. Matching of hypergraph H is a set of independent edges in hypergraph H. A K matching is a matching consisting of K edges. Let V of H denotes the maximum cardinality of matchings of H. We denote by MHK the number of K matchings of hypergraph H. John introduced the polynomial phi of hx of a hash tree H and obtained some properties between the eigenvalues of H and this polynomial, where the polynomial phi of hx is defined in this way. We in this paper redefined the matching polynomial of H in a very similar manner. And we give some basic properties of this matching polynomial. These two results, these two recursive formula for matching polynomial will be used in several times. The matching polynomial of hypergraph G is equal to the matching polynomial of the hypergraph G minus 1 HE minus the matching polynomial of the hypergraph obtained from G by deleting our vertices in the edge E. If let U be a vertex of hypergraph G, and I denote the site of L subscript I adjacent to U. For subset G of I, we have this formula. The matching polynomial of G is equal to the matching polynomial of the hypergraph obtained from G by deleting these edges minus the sum of the matching polynomials of the hypergraphs obtained from G by deleting vertices in the edge EI. In particularly, we have this formula. The matching polynomial of hypergraph G, it can be expressed as x times the matching polynomial of the hypergraph G minus vertex U minus the sum of matching polynomials of the hypergraph obtained from G by deleting our vertices in edge E. We introduce the matching polynomial method. We first introduce an ordering I on hypertrace, and then we find the ordering of hypertrace is compatible with the order of their spectral gradient value. The determination of the ordering of hypertrace is usually easier than comparing their spectral radius directly, because we can use the two formulas, the two recursive formulas we just mentioned. Additional tools for comparing spectral radius of hypertrace can be obtained with matching polynomial methods such as H-grafting theorem. Matching polynomial method can combine with other tools such as weighted incidence matrix method, the method posed by Professor Lu, edge-moving theorem, and so on, tends to be more powerful. First, we give the definition of order ring on hypertrace. Let T and T prime be two hypergraphs without cycles. So it in 2018 defined the ordering and follows. If for array x greater than or equal to the spectral radius of T,
I'm sorry, I'm too busy at the moment. Thank you very much. Goodbye.
If for array x greater than or equal to the spectral radius of T, the matching polynomial of T prime minus the matching polynomial of T is non-negative. Then we say T prime is no more than hypergraph T, hypertree T. If T prime is no more than T, and the point and this polynomial and the value of this polynomial and the point x equal to the spectral radius of T is non-zero, we say T prime is strictly less than T. From the properties of matching polynomial of hypertrace, we know that T prime if T prime is less than T, then we have this result: the spectral radius of T prime is less than or equal to the spectral radius of T. If this inequality is strict, then this inequality is strict as well. Now we introduce the definition of edge-moving operation. An edge-moving operation on hypergraphs were introduced by Professor Qi and Professor Shao and me in this reference. Let H be a hypergraph with a text U and edges E1 up to EK, such that E is not in EI for I from 1 to K. Suppose that VI is in EI and right, and we construct new edges EI prime from in this way. We delete this edge EI prime is obtained from EI by removing its vertex VI and adding a new vertex U. Let H prime be the hypergraph with the same vertex V and H set E prime. E prime is obtained from H set E, replacing K edges E1 up to EK by the K new edges E1 prime up to EK prime. Then we say H prime is obtained from H by moving edges E1, E2 to up to EK from these vertices V1 up to VK to vertex U. Edge moving theorem. Let H be a connected and uniform hypergraph. H prime be the hypergraph obtained from H by moving edges for no multiple edges. If X is a principal eigenvector of H corresponding to the spectral radius of H, and suppose that XU is greater than or equal to the maximum. XU is the maximum among these components. Then the spectral radius of H prime is strictly larger than the spectral radius of H. Okay. Two notations. We use RT1 up to TL to represent this hypergraph. And RTAB to represent the right one. Now we define some types of edges. Let T be a non-trivial or uniform hypertree, and U be a vertex of hypertree T. We consider such edge E incident to U, satisfying that the edge incident to those vertex other than U or only pendant edges. Let A be the number of support vertices in this set. We define the edge E to be L type if A is 0. Equivalently, E is a pendant edge. E is F type if A is positive. Edge E is F bar type if E is F type and every support vertex is of degree 2. The edge E is W type if E is F type and A is equal to R-1. E is W bar type if E is F bar type and A is equal to R-1. E is a W hat type if E is W type and just one of R-1 support vertices is degree more than 2. E is K type if E is F type but not W type. Edge E is K hand type if E is K type and A is equal to 1. First, we give some lemmas. Let H be any R uniform hypertree. Then for any non-negative integer S is greater than or equal to 3, and T is less than or equal to R-2. These hypertrees, right? These hypertrees, the hypertree in the left is greater than the hypertree in the right. The second lemma, let H be an arbitrary R uniform hypertree. Then for any non-negative integers S and T, the hypertree in the left is greater than the hypertree in the right. For every hypertree T, if C is the site of some independent core vertices in T, then there exists a maximum strong stable set. Strong stable set, a subset of vertices is strong stable or independent if no two of these vertices are adjacent. For every hypertree T, if C is the site of some independent core vertices in T, then there exists a maximum strong stable site such that C is contained in this site S of T. We will skip these lemmas. One of our key lemmas is this. For any hypertree T in this site is associated with integer D. D is greater than or equal to 2. Then there is a hypertree in this site. This site is associated with J is 0 or 1. There exists a hypertree in this site such that it has larger spectral radius than any hypertree in this T. Our main results are to characterize the first two hypertrees in this site. This site is the site of our R uniform hypertrees with M edges and strong stability number alpha. We introduce the notations like this one. We use the hypertree A to denote this hypertree, and the notation B to denote this hypertree. We shall show that these two hypertrees are the first two hypertrees in this site. These some lemmas we needed. In this site, B uniquely has the largest spectral radius. Note that the hypertree A can be obtained from hypertree B by applying edge moving operations. So this hypertree A is greater than hypertree B. Thus, we can obtain our main result in this site TMR alpha. These two hypertrees A and B uniquely have the largest and the second largest spectral radius. This is our main result in this talk. Thanks for your attention.
Thank you very much for a very interesting talk. Any questions, please, to the speaker? I have a small question. So, due to your talk, all results were obtained for hypertrees, right?
Yes.
Which means that you consider hypergraphs with no cycles.
Yes, with no cycles.
But do you have any results which were not included in your talk, but they are due to hypergraphs having cycles?
Yes, but to use our matching polynomial method, we matching polynomial method is useful and correct for hypertrees.
Only for hypertrees?
Yes, only for hypertrees.
So for hypergraph with cycles, you use another theory. I mean, another approach.
Pardon?
Well, I mean, you said that you have some results concerning hypergraphs with cycles. Does this mean that you have another theory, another approach for that result?
I still I don't understand your question.
Well, okay,
Can you-
don't mind, please. Yeah. Okay, I will ask you just later. Okay. Any other questions to Honghai Li, please? Well, if not, then let us thank again our last speaker of this session. And I also would like to thank all today's speakers as well as all speakers of this workshop. Thank you very much for all of you to join us for this workshop. Thank you very much for participating.